see. Yes, I think I can. Okay, cool. Hello. I'm Ryan. I've given a couple talks here. I do a lot of compiler research for fun. I do work at Starbucks as a day job, but a lot of the time I don't spend much time thinking about work. I mostly think about compilers and just formal verification stuff. This talk is something that I've been wanting to write a blog post about for a long time, but I haven't kind of found the words to be able to do it. So just like as a warning, this is like kind of a beta blog post, and I think that I can give a talk and I think I can make this good, but I am just going to warn you ahead of time that the examples might not be like the best and there might be some talking through. If you have questions, feel free to stop me at any point. The feedback that I get from this, like from you guys asking questions, is going to help me kind of shape kind of what I do. So I came to this title because there's this thing called like invariant based programming where you have these like preconditions, you post conditions, and there are some languages that kind of support this thing that generate asserts for your preconditions, your post conditions, to make sure that your functions work like you would expect. That's not what I am interested in talking about with Go. I'm sure that there's some sort of invariant based programming framework for Go that you could go find. I'm just kind of more interested in the fact that like this idea of an invariant, which I'll get to in a second, is kind of really pervasive in code. And there's a lot of advice that is given to junior engineers, like you need to comment your code, or you need to like kind of make sure your code is flattened. You need to make sure that your code is readable in such a way that I can kind of understand what it is. And I feel like that can kind of be vague for some people sometimes. And I think that kind of, oh, whoa, what happened?
Yeah, that's the thing. Like everybody just kind of gets kicked off if they're idle for 5 minutes.
What am I going to do there?
If you rejoin in the meeting, you can reshare it. You probably lost your Wi-Fi.
Oh, I'm connected to Wi-Fi right now.
He's presenting. Plugged in with the
Ethernet. Yeah.
Then you should be on Wi-Fi.
I'm pretty sure it's Ethernet, but oh well. Okay, well, hopefully we don't have too many of those. Okay, so yeah, so let's talk about what an invariant is. So it's a property about some program, like whether like this be a like it can be a full program, like a function, it can be a variable, that's something that doesn't change. So I have some code up on the screen, and I would like to talk about this. This code is really good for talking about invariants. So we have this really simple, it's integer division. I'll tell you that it's integer division. So you have A and B, which are constants, and you do this integer division, and then you print A, B, and Y. There's something that's true about B here, which is what? If we run this code here, what will always be true about it? If you want to make like a guess, there's something always
B
true.
is not 0?
Yeah, B is non-zero. Thank you from online. Yeah, why? Well, if B was 0, then what would have happened? Right? So it will always be 0. So if we run that, it will be 0. So an invariant of this program is that at this line of code, this is another thing to think about. At this line of code, B is going to be non-zero. It's just not going to happen. So there's a lot of ways of enforcing invariants that we'll get to, but let's talk about some problems they solve. So just like I said, commenting code. So a lot of the times I'll see commenting code where the code that gets commented tells me what is happening to the code. I see someone increment something and they'll say increment counter. That's not very particularly helpful for me. I can see that the counter is being incremented. Thank you, counter plus plus. Very helpful, right? Whereas like if we talk about the invariant that B is not 0, that's more interesting to me because you're going to start doing, maybe you start doing more divisions with B. And that's interesting to me as someone who's reviewing your code and someone who maybe doesn't entirely understand the code base. I'm starting to kind of understand more what is going on because you are commenting why certain invariants exist and why you can take advantage of these things. The other thing is preventing data corruption. Like obviously you want like, the data that you write to disk to, be safe. You don't want, your data structure to get messed up. If you have a balanced binary tree, you don't want that balanced binary tree becoming unbalanced unless you're asking for it. The other thing is that like when you kind of think more from the invariant side of things, you're proving to me that your code is correct by the code itself. So when I see a lot of people who are who kind of have a lot of ifs, your like control flow is all over the place, I struggle to kind of keep in my head everything that's going on, and I struggle to figure out if your program is correct. You can test it, but that's not very helpful to me. I can see your tests and maybe they're helpful, but like that doesn't give me necessarily the argument from a code reviewer's standpoint that it's correct, and I have to spend a lot more time working on it. So debugging with asserts, like throwing like assert in there to assert certain invariants is really helpful when you're building really complicated programs. You maybe want something to be non-zero all the time, and so you just say assert not zero, and if it ever is zero, it will fire off an assert and panic or fail or whatever it is. And then the last thing is performance. So back into the compiler round. So there is a pass and go called prove. And prove sits there and it looks through all your control flow, and it looks at all your variables, and it tries to prove as many facts as it can about your code. And then what it does is it takes that and it uses it to optimize your code. And so if you can teach the compiler that these are the invariants that I have in my program, I promise you that that division is never zero. I promise you that there's not going to be a division by zero. Then that what's it called? Then that check for zero before it actually does the division will go away. So thinking about invariants while we're doing that can have quite a few, or like while we're coding, can be quite beneficial. So like when you actually enforce an invariant and you say like, this is a thing that I want to be true about your program the entire time, there's a few like ways that I've thought of to do this. One that I like to think about a lot, or I like to see a lot in code, is this if condition return your thing, and then after your if, you've returned early, this not condition must hold for the rest of the program, right? So in this case, if we were to say if error equals nil, return this thing, down here, we can now use error. We know it's not nil, right? And we can start using error. And we know that it's not nil, and there's not going to be a nil check that gets generated or something. And so that's really nice, right? That we have this way of teaching the compiler, this way of teaching everybody who's reading our code that, hey, this thing is not going to happen down here. And so don't worry about it. You can actually start reading the code. And the more of these kind of returns that you have, or the more kind of data manipulation to get your invariants in place at the start, the better that you're going to have, or better time you're going to have reviewing code, or like making sure that, or testing it. The other thing is like, you do a lot of number theory here. So like we work with 64-bit integers, 32-bit integers, right? Those are bounded, right? So they're not infinite. It's not, infinite precision. We're not in Python. And so, using the modulo operator, you can kind of bound things in really easily. And, you have two's complement wrap around. So when you have negative integer and you increment past them, you can maybe use some two's complement as well. And so number theory can kind of come up a lot of times where if you're smart about things, then you can make things run quicker, or kind of more correct, or you can kind of see why things are correct. And then the last thing is synchronization. The synchronization gives you a really cool invariant, which is anything that goes on inside of like a mutex, it must the current state of the critical path, like counter, everything must have happened before. Like if counter is 1, then it must have been incremented before you take the mutex, right? So it creates this happens before relationship, and it allows you to kind of now enforce kind of harder invariants on your program, saying that, hey, this is a property that we want. We want this thing to happen before this thing. That doesn't, I'm not saying ordering. I'm just saying that it lets you know that something has happened before another. That's not event ordering, that's different. So kind of being very invariant aware, I think, is where I'm kind of interested in seeing a lot more programmers kind of grow. One thing that I, like a mentor of mine did in college, he would kind of put up a piece of code on the screen, and then he would walk you through and he'd ask you kind of what the invariants are at each step of the code and asking you what could possibly be true at any particular time. And when you do that, you start to kind of understand all of the sets of inputs to your program, what could happen, and all of the outputs that could happen. And then you learn how to restrict those things, because we don't have, already we don't have infinite inputs and infinite outputs, but we want to make our code easy to read. We don't want to complicate it more than we have to. And so restricting the input space, kind of making it easier for us to use, and restricting the problem space is really helpful for kind of being invariant aware and making sure that you can enforce these invariants, keep things correct. And then trade-offs with lazily enforcing your invariants versus eagerly enforcing your invariants. And a good example of this is, I guess it's not exactly invariant enforcement, but when you add, well, I guess it is. So if you append to a list that does not have capacity inside of it, the naive approach would just be add one to the capacity and copy everything over. But we know that that's actually really slow. You end up creating like an insertion time of that's way too high. I think it's like n or something rather than like an O of 1 insertion time. Whereas if we enforce it by widening the like doubling the list size, and we say that like, well, we can now enforce it for a lot longer, and we're kind of lazily like waiting for this variant. There are kind of complicated data structures where you can get away with, doing a lot of insertions, and then when it's time, then you can ask it to enforce all the invariants, and it will enforce all the invariants for you. And that kind of amortized complexity is really, really helpful when you're dealing with complicated data or complicated data structures, so you can amortize your invariant enforcement. So for performance, we want to teach the compiler kind of what's up. And that's kind of how we can squeeze performance out of a lot of our programs. So we want to teach the compiler what sort of things are invariant in our program. In this case, I want to find the first item that differs in this list, in these two lists. Unfortunately, we don't know if these two lists are the same size or not, right? So we probably want only the smallest size here, and then we can look through the list and then return the index that we find it at, or we'll just return the length of the list if we didn't find anything. So the problem is with this piece of code is it looks really nice, but Go is not this smart. Go, unfortunately, is not smart enough to realize that the min of len x and len y inside of this I will eliminate bounds checks on these, right? Because it's true that if we take the minimum of the two, that we're using the smaller one, and we should not have bounds checks on either the bigger one or itself, right? So instead, what we can do is we can teach it. So we can enforce some invariants a little bit harder. So we say, okay, well, if the length of x is less than y, we're actually going to swap. We're going to tell, this is a way of telling the compiler, like, hey, I want the smaller one to be inside of the bigger one to be, is that right? The bigger one to be inside of y or inside of x? Because len x is less than len y, then it's the bigger one.
Yeah.
Right. Yeah. And then you do this thing. I don't know if anyone's seen this, but this is like a bounds check elimination hint to the compiler. It says that, hey, let's do this bound check up to len x. If there's not, if this slice doesn't work, then it panics, and the invariant that all bounds checks within here are going to work will hold, because it will panic here. And then we get to eliminate a bounds check off of these two array lookups. So by enforcing this invariant that, hey, we're going to pick the smallest one, and we're going to run through it, you get rid of these bounds checks. Yes.
So just be clear, that line of code will never actually panic because of the previous line of code, right? Like,
yeah, that's true. That is also true. Yes, it should never panic.
but the compiler knows it would panic, so it can eliminate the bounds check.
Right. Yes. Yeah. So, okay, cool. So correctness, I think is my next slide. Okay, has anyone seen the binary search problem? Like why most binary search problems are actually implemented incorrectly? There's a really subtle bug here. And it's kind of hard. So this is like a standard binary search, right? So the idea is that you choose some midpoint between your low and high, and then like you do a comparison, you see like, am I to the left or to the right, right? And then you bisect, you move to one side or the other. And then eventually you either return mid or you return, like this thing down here. But there's a subtle bug here, right? Which is like, has anyone, you've seen it, you seem to know what the issue is. What's the issue? You know? Yeah, you seem to know what the issue is.
Like, I remember if low less than or equal to high 3 equal might never terminate.
This might not never terminate. So why might it never terminate? There's something in here that makes it so that it won't. So it's this line here. So there's a problem. So if the haystack has about 1 billion elements in it, which I know that sounds crazy, but it happens. If we were to like remove this and we were to say it's a database, right, where we're like binary searching over pages, right? 1 billion elements is common. So the problem is that low plus high overflows. And so you might not have this ever finish, because if low plus high overflows, it might just get caught in a really weird loop where low is never less than high. So what's the deal here? Like how do we enforce kind of this invariant that low plus high is never overflowing? You just convince the compiler that, well, you don't have to convince the compiler of anything. Convince me that it doesn't overflow by saying, well, we had signed integers. What if we just use unsigned integers? And then we divide by 2. We're getting an extra bit in our bit width, and then 2 unsigned integers, 2 signed integers added together will never be bigger than like that extra bit, right? So you don't have a problem. And then you can divide by 2, and then you can convert it back into an int. And you have done things correctly. So I guess what I'm trying to get across here is that you have to, like one, math is tricky, right? Like the fact that it overflows is kind of like weird, and most people won't run into that. However, people do run into it, and you should really be thinking about how addition overflows or how your numbers work, and being able to correctly kind of enforce these invariants in such a way. Like you could do like a bunch of crazy math that doesn't like convince me that this is correct. You could do like some weird like low subtracted by high plus low divided by 2 sort of thing. There's another way of formulating this, but being able to kind of concisely enforce this invariant by saying that, like, look, we're going to widen things up a little bit. We're going to be within 2 to the 32, and this is how we're going to kind of handle this overflow case, is something that I don't see junior developers doing a lot.
Or developers in general.
Or many developers in general, right? Okay, this one's complicated, so I'm sorry, bear with me. Simplicity, right? So a lot of times I grabbed this code from a site called Exorcism, which is kind of like a leak code-ish site. This is like a community solution to a problem, which is verifying ISBN numbers. So ISBN numbers, it's pretty simple to verify an ISBN number. There's a bunch of dashes inside of the ISBN. Don't worry about the dashes. You only need the numbers, and there should be 10 numbers, and those 10 numbers should add up to something that's divisible by 11 with this equation that they have. Like you take the index of current ISBN number, and then you multiply it by the number itself, and then you mod it by 11, and it should be 0. It's a little checksum sort of problem. So we need 10 numbers. We need the last one. Oh, and there's a special case. The last number, the last digit could be an X. And X means 10 in this case, because you can't represent 10 with a single character, right? So we have X as 10. So we need to somehow take all this string that we're given, and we need to verify that it's a valid ISBN number. So convert, this person decided, we're going to convert into, convert it to an int. If it doesn't work, then we'll check to see if it's an X. If it is an X, then we'll just append 10. And notice that they are prepending here, because you do have to kind of work backwards when the equation, I should have just put the equation on here. You do have to work backwards. And so their way of solving this is prepending everything, making sure that rather than having, the list in order, like the ISBN number in order, they're reversing it, right? So in order to kind of do this calculation, they're deciding that reversing is the correct thing to do. And then notice that anytime they see a dash, they're bailing, anytime they see a dash, or if it's not a dash, right? The only character it could be is something that's a number, an X, or a dash. And this is how they're trying to enforce these sorts of invariants in the code. You see, like okay, we're getting nods, so that's good. Okay, so this is a little complicated though, in my opinion. When I'm reading this, it's not very clear to me that all of the things that I just said, that you have 10 digits with some dashes in it. The dashes don't matter. Everything needs to add up. This equation here needs to add up to something mod 11 being 0, and there needs to be 10 numbers, and there's a potential special case of X. That doesn't tell me this. If I reviewed this code, I wouldn't know without an extensive test suite of what's going on, because the way that they're enforcing the invariants, they're not thinking about it too hard. They're just going they're starting the program, and they're not thinking about how we can efficiently and kind of simply enforce these invariants, right? So I wrote one. This is mine. So I just get rid of all the dashes out of the way. Just get it. Then I split it up by character. And if the last element is an X, then I just turn, because they're strings now rather than characters, I just turn that string into 10 because I know that that's what it is. And then all I do is I do the same exact thing. Notice I didn't have to prepend the list because of this. I'm just taking part of the equation is that they want the index counts down while you're summing up forward. You're counting down this way. You're multiplying by 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then on the way up, your indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8. So it creates a problem, right? So they're prepending to the list. So this is trying to say is that notice that I enforce my invariants. I return false very early. I keep everything very flat. And my idea is that once I get to this list, I'm doing exactly what I'm supposed to do. I could even separate this out further, and I could just map this list into integers first, and then there would be no error case inside here, and it would just be this list. And so the idea is that now it's a lot easier for me to review, not just because I wrote it, because that does make it easier, but it also makes it easier to know that all the things that I have been asked of me to verify, I can verify them. And it's very easy and straightforward to read. But lots of people will kind of just complicate their invariant enforcement. Yes.
I was going to ask, do you have any intuition as to if there's performance gain here as well? Is there any sort of I know you mentioned that if you can give the compiler enough information, it can get rid of work. Did you benchmark these at all, or I'm just curious?
I mean, the inferiors is slightly less performant, but only slightly.
Those appends have got to be hurting.
I was gonna say the appends are killer. Those appends are nasty. Yeah, because you're copying, you're spreading. So
You might,
what do you mean? What's the cap of this?
Yeah, the capacity.
What's the cap of a single? It's 2, right, by default, or is it 3?
That was 8 by default. So
8 by 5. Well, we're getting a bunch of different answers.
I have no idea.
Okay, and then it still has to grow it at some point. So the capacity is 5 every time. So once this becomes,
Fibonacci.
oh, is it? Oh, okay. So once this gets bigger than 5, though, it will be a copy every single time,
Right. It wasn't 5. It's Fibonacci.
right? And then on top of that, they're always parsing this no matter what. Even if it's an X, right? They're always parsing that, right?
Yeah.
And then inside of your hot loop, and then they're doing, so notice they're doing 2 loops. I'm doing the same thing. I'm doing 2 loops, right? Notice I'm doing 2 loops.
You'll never check the length.
My loop is, they do at the end.
Oh, do that.
They do at the end, which that's another thing. Right?
Oh, I missed that.
Yeah, they do at the end. Right? Okay. So, but I
After the calculations happen, then you check to see so you could calculate 1,000
yeah,
numbers to get the sum and then ignore that sum.
Yeah, exactly.
Yeah.
Well, and so notice here too, though, that I check this and look what I index. I just straight index here. Like most people tell you like, ooh, don't index, right? Don't index like hard-coded index into arrays. But notice I do this and I am immediately convinced that this does not panic, right? As a reviewer. And like this right here is my loop there's a loop here that filters it out. There's a loop here. So I guess I get
You're
three.
calling into someone else's.
Right, I'm calling into someone else's loop. So there's 3 loops here versus their 2 loops. But like, okay, like there's probably more performant ways of doing this.
It also depends on how many instructions. it
Exploit
costs to
is your
copy.
problem. Huh?
It also depends on how many instructions this costs to like copy, because they might expand it in place, they might not.
Right. Yeah.
Depends on the allocator. Like there's a lot of unknowns. They're close. It might
It's,
also be architecture dependent.
Yeah.
let's be honest, it's massively more readable, and that's more important to 99%
Well,
of
and
people.
it's,
than
so
the performance.
it's readable and it's clear to me what to test here.
Yeah.
If I'm handing this to someone to test, they can go like, oh, here are all code paths that I need to test, right? Yeah, go ahead.
I'm also curious, because I agree, I think that readability is far more important. But in the previous slides, you used splicing to let the compiler know, like, hey, you don't have to check anymore after this point.
Yeah.
Whereas in this one, you're just saying like, hey, I'm gonna check the length in an if statement and the return. Is the compiler smart enough to know it can align bounds checks if that happens, or do I need to also slice there?
You don't need a slice. Yeah, it understands. Yeah, very nice. Pretty sure it understands. That'd be so absurdly bad if it did not understand. Because the bounds check, so prove goes through and it will see the ISBN is the length. Oh, actually,
This does not equal
maybe-
10, so.
actually, no, it will bounds check it because not equal to 10. Do you know what? My implementation is wrong. I wrote this like 45 minutes before this talk. So I apologize. This should not be not equal to 10. It needs to be something else. It needs to be like greater than.
Probably needs to be bold.
Well, if it's less than 10.
If it's less than 10, you return, and then you also say it has to be exactly equal to 10. So
Yeah.
it's not more than.
Yeah, if it's yeah. Anyway, sorry about that. But if it's an extra line of code, sorry. Man, look at me go. Okay, so it happens, right? Okay. Oh, actually, any last thoughts here before I move on? Okay, so here's another one. Here's another fun one. So when we have data structures, right? So I'm not really interested in the actual invariant enforcement inside of this data structure here. I'm not really interested in it. I'm really more interested in what data structures we choose in here to actually make the insertion happen with this linked list. This is a linked list. It's generic because we have generics in Go. And this is kind of like the classic linked list insertion that you'll learn in college. The problem is that upon inserting a node, we don't know if this head is null or not, right? And so we enforce our little, and we just make sure that we're not accessing any null pointers here. Because this next part, we're about to start doing some null pointer accesses, possibly. We're gonna start with the current thing, and we're gonna keep getting the next item. No, I didn't mess that up too. For a second there, my goodness. We're gonna keep getting the next thing. This thing could panic, right? Theoretically, but it won't because we took care of this, right? This should run until it hits a next that's null. And we're using this previous to kind of keep track of the last one that we just talked with, right? So this is a kind of a cute way of trying to, enforce that you never cur.next into like a null pointer, right? This is solid code. I'm not trying to say anything bad about this. This is good code, right? Okay. But if we're a little bit more careful about our data type or data structure choice, we can do a little bit cooler than that. So this is my implementation. If we instead use double pointers instead of single pointers, then we don't have to do all of this head list check.
Talk about readability.
I did.
Writing a linked list.
No, I get it.
I think
I will take the heat for this one. I understand. I think this looks better personally. But to me, it's very clear that you're not ever going to access a null pointer and you're not double checking it. You're only checking it once, ever. And this loop is just so straightforward for me to read and to check that you have not accidentally accessed something. You're kind of doing this weird shuffling over here. That's hard. Again, I think I'm just, to be honest, people think I'm smart. I'm really dumb. I really want just really straightforward code to read. I can't make heads or tails of whether something is right or not. Like just super quickly. I have to like really think about it. So okay. So with the double pointer thing, I know it's complicated. Just bear with me. But the idea is that you can take a pointer to where you want to put the node, which is going to be the next, right? But it just so happens that like kind of our next is our head as our initial case. And so if it is null, if head is null, then we just, since we have a pointer into the field on the struct, then we can just dereference it and assign it. And we have completely removed all null checks and weird shuffling. We have made it very straightforward to read that like we're not dereferencing null pointers here.
Put another way, you're limiting the edge cases entirely.
I have completely eliminated all my edge cases by data structure choice. I know that a double pointer doesn't sound, it's a data type. I don't know. It's just, it seems like a data structure to me. I don't know. It seems like a good choice.
The surprising part to me is that you can get the address of nil.
It's an address to a field that is nil.
Okay.
Right?
I guess you're right. Okay, yeah, I see what you're saying.
Yeah.
Yeah, okay, that's different.
Cool. Okay. Cool. Yeah, it's
One of those in the C days, this would have been in like a
This is the Linus.
or a file that would have been like, if you don't know what you're doing, stay out of this file entirely. Ask someone more senior.
This is a Linus Torvalds thing. And yes.
So are you okay if I nitpick just slightly?
No, flame me. Go ahead.
Technically, L can be nil.
Okay, sure. Sure. Yeah, I don't like that about L. I don't like that about Go. Sorry. This is really weird to me that L can be nil. Yeah, I guess.
I really should check this all the time, and I basically never check them.
I mean, you know what? Just because you said that, you know, I could just take that pointer out because we're using, huh? Actually, we can't. Yeah, because we're modifying the structure.
It's not exported. You've got to have a thing that has a B table to look up in the first place. So you've got to instantiate a linked in the first place.
Oh, I see what. Yeah, you. Wait, do you?
You're technically correct, which is the best form.
Okay, I'm gonna just believe that Todd because he's.
I would trust Todd over me. So.
Well, it's not exported, so you can't call this. Is what the real point.
Oh, I see what you're
yeah.
saying. Yeah. I agree. Yeah. I'm not enforcing all the invariants. I agree with that. L could be nil, but honestly, if L is nil, I want it to panic. Please panic. Actually, that would be really bad. Okay. This is, I guess we're getting, oh, do I have another? No, that's the last slide. Okay. So this last thing, synchronization. So one thing that I see a lot is, the lack of synchronization, in code, or people just like access things multi-threadedly, or don't explain to me why it is the case that using atomics work is another really fun thing. I think that in general, kind of using your synchronization in order to teach me about what code is doing is a really good idea. Because I think, as I mentioned at the beginning, so if we have two threads that are, one's trying to read and one's trying to write counter, when we have these locks here, this is telling me that once this lock happens, that anything that is in counter right now has happened before I am reading it. And in fact, there is not anything happening to it either. Those are your two invariants that you're enforcing here that I like to know about. And your locks are telling me very clearly that that's the case. You could use atomics. You could do a lot of other really crazy synchronization primitives. That's fine. I really like locks though, until it becomes a performance issue, because it's very clear to me what this does. It's very clear to me that anything that has happened to counter has already happened to counter. There's nothing going on with it. And the same with counter up here, right? Is like when you, because this is doing a read of counter, and then it's doing an increment and then a write, right? Counter plus plus. And so making sure that X happens before Y. That's kind of like a big deal, is that X is like some event has happened before another event. That doesn't mean that the ordering is correct, right? This lock could lose a bazillion times to this one. But once this one wins, then you're telling me what's going on. So a lot of, this is where I'm not entirely sure how to kind of get my point across, that when enforcing invariants, when it's in a multi-threaded environment, there needs to be some sort of concurrency or some sort of synchronization primitives around it, convincing me that your code is correct, right? Because I think that that's kind of my whole point with this invariant aware programming, is that lots of code is just like really bad spaghetti. It does not convince me. Code should be convincing to me that something's correct. When you look at it, when you code review something, some people should be convincing you that your code is correct, right? Or that their code is correct. Not just, here's this code, have fun, spend a couple hours on it and ask me questions if you need. And I think too, then you can start this is kind of self-documenting about the happens before, but it makes these sorts of invariants that you enforce are much easier to document and tell me what's going on than, incremented counter on this, putting a comment in here. That does not tell me what's going on. It's like, no, this counter could be accessed from another thread, so I'm locking it so that I can do that, right? That's a good documentation thing. Lots of people don't think about it in that way, though. They think about documentation as kind of something to tell you what the code is doing, not why the code is works the way it should, which is kind of lacking in a lot of software circles. Anyway, I think that is it. I thought I might have another slide, but I guess I must have removed it right before. So that's it. Any questions? Is that all?
I'll say one of my favorite versions of this that you don't have on here is Go's switch statement. And my favorite because they made the very smart idea to not have fall through be the default, which I find to be tedious in every other language. So I guess you'd have a switch there. I was thinking more in the first example you had with the binary, what's the binary search? No, it wasn't the binary search.
ISBN maybe.
ISBN, yes. So you had the ISBN example, right? And if I had looked at that, I probably wouldn't, yours is better, but I would look at this section in the for loop and say that if else is almost always more readable as a switch to me personally.
Yeah, I would agree.
And because you can look down the list of cases and go,
Sure.
I know all of the.
Well, so even if it were, so I guess my question is is this convincing to you that it's not checking any other characters other than numbers? Are you convinced that this is making sure that other characters that should not be there are just briefly looking at it? Are you convinced that no? It's very hard, and I've convinced myself that it is actually doing that because I've had to read it. I sat looking at it for a really long time. It does, but it's not very convincing to me that it's right. And I guess that's kind of what I'm hoping to get across to everybody tonight, is that code should be convincing of its correctness, not necessarily just something that you do and handle these edge cases. You need to be convincing. Right?
Well,
that's what code is convincing someone that it's correct.
Right. And I'm just saying, maybe an interesting example, a really low early on example for the slides that I think would be Go's switch, because you do get to look at all these cases, and every time you pass a case, you've got an invariant
that you have enforced, right? Yeah.
Right? And you can do as many error cases, right? It's error, this kind of error, that kind of error, that kind of error. It's a useful readability tool.
Yeah, that was one thing that I thought of kind of last minute, was doing error handling in this talk, just having a lot of doing a lot of error handling, a bunch of switches with error handling, because that is a way that I at work enforce invariants. I had these big switch cases that are checking a bazillion things, and so that I can make sure that at the end of the day that my code is doing what it's supposed to in the happy path. So
A lot of this talk is very much what are you conveying to your audience as a reader? It's very much like a writer-reader relationship, not really about code as much as it is about not even readability, but like what your audience is. Like the double pointer thing, like that doesn't scare me, but I started to see in the 90s. So
Sure. Yeah, it just scares most people. I understand. I was trying to come up with good examples and everything was more complicated than that.
yeah, so this is like one of those like scenarios where knowing your audience is also super important to conveying that correctness.
Yeah.
Which is, I think, lost to your first point in this talk. I think it was very much lost in the discussion about like code readability, self-documenting, all the nonsense buzzword that we talk about.
Right.
It's like, no, at a glance, can you tell what this does?
Right.
Some of that's naming, some of that's like style, but a lot of it is like, are you using the constructs that your audience actually understands?
Correct.
And, you know, so like the double pointer scenario is a really good case of, if you have, you know, 5 other people on your team and they all know this stuff, that's perfectly fine and
Sure.
reasonable.
Right. But when
If
you're not.
if you have a bunch of juniors, you're going to be spending a lot of time like, okay, you're going to need to learn pointers
Right. Yeah, I agree. And I think that
or just stay out of the spot.
Right. I also need to hammer home more that like the thing is that when you do these like clever little tricks or you actually enforce invariants, that's when good documentation can help a lot in cases where it's like I have to do something clever. I apologize. I am about to do something clever. And that's when the documentation comes in. And I'm not saying self-documenting code, by the way. I don't believe in that. I do believe that you need to tell me why.
I said
you're
we
doing
as a
Right, yeah, I agree. Right. I think that, yeah, you do need to like, when you actually enforce invariants and you're not just spaghetti, throwing things at the wall, trying to see if they stick and see if I actually hit all of my edge cases, that's when the documentation really starts to shine, where it's showing me that like you are handling all the cases that you could be having and you're telling me why you're handling those cases.
Yeah.
Whereas like when you tell junior developers to document things or developers to document things, you just get a lot of random crap and it's like lots of comments that are not helpful. Whereas when you start, and then like once code changes, then that goes away lots of times. But with invariants, it's a lot harder. It looks very clearly wrong when you are changing how you do things, and then you have the wrong documentation, and you're like very like explicitly like these are the things that I am trying to handle. These are the requirements that I've been given. This is what I'm handling it. This is how I'm handling it. The minute that your documentation gets out of sync, then you start to feel it, and people start to see it a lot easier than if you just put a bunch of documentation there that is useless and doesn't say much, because when I read that and you've changed the code, I don't know if that documentation that says much anymore.
Yeah. There's an aspect of this that I think I would never bring up outside of this room, let alone if I was giving this talk somewhere else or something. But like, I know the first guy that I ever worked with that was a TDD zealot,
Yeah.
programmed very explicitly like one test case at a time, adding layer upon layer of those requirements. And like, I mean, it was in Python, but very much a clear invariance based kind of direction. And I think that might be the only way to do TDD correctly or usefully.
Right.
And I find a lot of resonance there, even though the religion side of it is not particularly helpful.
Yeah.
I see the parallels, and that's super interesting to me because of the value that some people get out of that versus like a lot of other people don't when they don't do it that way. It's really like the kernel of truth is really this invariance that you're speaking about and the readability of that.
Right. Yeah.
There's layers to this talk.
Yeah. I need to figure out how to like, again, drafts, try to figure out how to piece everything together. But
I like having extra words to describe why I like the flattening thing that you talked to me about like a year ago or something.
oh, yeah. Like code flattening. Yeah. See, that's the other thing, is that I could just give this talk about code flattening. This could have just been like why I like flat code, right? Because I mean, it is like you can see that's flattened, but I don't necessarily like flattened code. I'll have else's. I'll have other crazy things, so long as it can convince me that things are going the way that they need to.
Yeah, this gives me a more accurate description of why I might choose to use an if and an else and all that jazz.
Right.
Which I think is useful.
Yeah.
I just want to say, I'm pretty sure this actually is correct.
Which one? This?
Yeah, that says that ISBN's length is exactly 10 to the compiler. We were talking about it, might be wrong earlier. I'm pretty sure.
Oh, it does. Yeah, it
I
does.
think you're right.
Oh,
It was
yeah,
also
I am right now.
when that conversation came up. It used to be 10. What do you?
I would like to correct the record. I was
Because
wrong.
I said at the beginning of the talk, not this is true here. So not this would be equal to.
Yeah.
Would be true here.
Yeah, length is exactly
Okay,
10.
I had it right. The compiler won't insert a bounds check there.
I love that we all trust each other's criticisms enough. That's that's a good crew. Awesome.
For the next 20 minutes.
Yeah, like my code must suck.
Yeah, you're right. I probably did it wrong.
Valid, I'm sure.
We've been
Wouldn't be the
live for
first time.
podcast.
Yeah, okay, cool. Okay. Sweet.